All right, we're going to solve some differential equations by separating variables. Let's start with what that process is all about. So the first thing you're going to notice, you're going to have a differential equation, which is nothing but an equation with derivative in it. And this equation here I have is dy dx equals 2x over y. And it's of the form f of x times g of y. And if they're multiplied or are factors, then you can use the method of separation of variables to solve this equation. Okay, and our goal is to get a function as our solution that's continuous and is in of the form y equals. All right, so this process is very simple. All we're going to do is what the instructions state, which is separate the variables. We're going to have the y's on one side and the x's on the other. And in this example here, I have dy dx, so I have an x on both sides with the 2x and the dx and the y on the left and the right. So we're going to multiply both sides by y, so we're going to get dy equals, and then we're going to multiply both sides by dx and get 2x dx, and then we're going to get our magic integral marker out, and mine's going to be a magic integral pencil. And then we're going to integrate both sides. And when we integrate both sides, we're going to get y squared over 2 equals x squared plus c. Now I could have put the plus c on both sides, but I am choosing to put one constant for both of them, and I'm putting it on the right side because the right side, eventually I'm going to solve for y, and I won't have to move the constant over. So we're going to leave the constant on the right side. And now we have to solve for y to get a function of y is a function of x. So multiplying everything by 2, we're going to get y squared equals 2x squared plus, now I could put 2c here, but 2c is still a constant, so we're going to leave it just as a constant here. And then we're going to have two possible solutions when we take the square root. So we're going to have y equals the square root of 2x squared plus c, and or we're going to have a solution negative square root of 2x squared plus c. Now, based on what our particular, this is the general solution here because I have a constant in here. Now, let's say I wanted to find the particular solution. Now, the particular solution is going to pass through a certain point. That's like an initial value someone is going to give you. So a particular solution passing through let's try 1, 1 because that's a nice point. Now, if I'm going to pass through the point 1, 1, my y is positive, so I'm not going to use this general solution because that's negative. I'm going to use this general solution because it's positive. So we're going to say y equals the square root of 2x squared plus c, but I'm going to use 1, 1. So we're going to say 1 equals the square root of 2 plus c, and squaring both sides, we're going to get 1 equals 2 plus c, c equals negative 1. So the inside of my parentheses, my particular solution will be y equals the square root of 2x squared minus 1. Now, if you would look, I've already done a slope field for this. And if I'm passing through the point 1, 1, we need to see, perhaps, if that will pass through my particular solution. Now, I have a program called the WinPlot that will allow us to look at our particular solutions. So let's do a slope field. So I'm going to hit equation, differential, dy dx, and I want my differential equation to be 2x divided by y. And I'm going to make the color of these things pink. And let's look at that slope field. So there's the slope field. And now I want to put my particular solution in there. So I'm going to add a point. We're going to add the point 1, 1. And I'm going to make it really thick so we can see it. Make the dot size 3 and make it solid. And let's make that black. There's our point. And I want to see if our particular solution that we came up with, I'm going to put our explicit solution in there, and that's going to be square root of 2x to the second minus 1. And let's see, we're going to make this pin density to 2 just to make it thicker. And we'll make this, what goes well with pink here, dark gray. And we're going to plot it and see if it goes through. Sure enough, and you can see that our solution actually will follow the slopes. And that's our particular solution. And you can see the general solutions shown in the slope field there, which is really pretty cool. All right, so it works. And I have in my notes here a picture of the very solution that we found. And it does pass through there, which is really, really neat. All right, moving right along. Of course, I would have to only choose this branch because for a function to be a solution to a differential equation, it has to be continuous, and clearly this is not continuous, so this would not be part of the solution. We'd have to restrict the domain for this, and it needs to be x is greater than 1 over root 2, greater than or equal to 1 over root 2, because 1 over root 2 will make this 0. All right, moving right along, let's do another one. Y equals x squared. Okay, well, y equals x squared. I mean, y dy dx equals y squared. I'm going to divide by y squared and multiply by dx. And now I have the variables separated, and I'm going to pull out my magic integral marker. There it is. And when I integrate this side, I want to rewrite it as y to the negative 2 dy equals the integral of dx. And when I take the antiderivative of this is going to be negative y to the negative 1 equals x plus c, but I can rewrite this as negative 1 over y equals x plus c. I'm multiplying everything by a negative, so we get 1 over y equals negative x plus c. And I'm going to flip this side. If I flip this side, I have to flip the entire side. So this will be y equals 1 over c minus x, and this would be the general solution. And if I wanted to find the particular solution, I would just use an initial condition and solve for what the C or the cupcake would be. All right, that was easy enough. Let's try another one. This one looks a lot more complicated, but it isn't really. What I love about this example is it illustrates that we have a constant over here. Now, it'd be really tempting to move the constant over, but we are going to have to get it back over here when we're solving for y. So I always leave the constants on this side so I don't have to move them back in the end. So I'm just going to move the y squared over and get dy equals 1/3 times x plus sine x dx. And I now separated the variables and pulling out my magic integral marker. This is going to be y cubed over 3 on the left equals 1/3 x squared. And the antiderivative of cosine is minus cosine x plus c. And now I'm going to multiply everything by 3. And we get y cubed equals x squared. Oh, I'm sorry, this is x squared over 2. X squared over 2 minus cosine x plus c, because 3 times c is just another c. And now we're going to take the cube root of both sides, and we're going to get y equals the cube root of x squared over 2 minus cosine x plus c, and this is again the general solution. Solving this, sorry about that. This was definitely x squared over 2. All right. Now, if I wanted to find out what the c was, I would have to have an initial condition, and I'd plug in for x and y and solve for c. Let's try another one. Stop and resist, resist, resist. Moving the 4 over with the y, because we're just going to have to move it back. So don't fall for it. We're going to leave the 4 over here. So we're going to get dy, if we separate the variables, over y equals 4 dx. All right. And then we're going to take out our magic integral marker and get, well, now this is going to be 1 over y dy, which is the natural log of the absolute value of y equals, if you integrate that, this will be 4x plus c. And now we're going to integrate both sides, or I'm sorry, not integrate, but exponentiate. So I need to get a different color to exponentiate here. Let's try blue. Exponentiating both sides. Now, when you exponentiate both sides, you're really exponentiating, and those are going. The 4x plus c will be in the exponent. Now, using the properties of logs and exponentials, we know that these are inverses of themselves. So I can bring the absolute value of y down, equals. And now I'm going to use the properties of exponentials and say that this is going to equal e to the c times e to the 4x. And I can do that because when you are multiplying with the same base, what do you do with the exponents? Well, you add them. So I'm going to unadd them and multiply them with the same base. Because now, believe it or not, all this e to the c is a big constant. And so I can say that the absolute value of y is equal to c e to the 4x. And I can drop the absolute value bars now because I can make this c positive or negative. Okay? And this right here is my general solution. All right. This form of differential equations used a lot in science, in mathematics, the finance of math, believe it or not. We'll find out in just a little bit here. All right, just a little bit has arrived. So when you see or hear the words, the rate of change of a population is proportional to its population. So let's see. Is this the rate of change? It sure is. The rate of change, and we'll call y the population here, the rate of change of y is proportional to its population. Well, this means k is the constant of proportionality. And so this is the rate of change of y is equal to k times the y, its population. So this right here is a differential equation. The rate of change of a population is proportional to its population. So we're going to solve this because this is very common in science. And so we're going to separate the variables, and we're going to leave the k, which is a constant, on the right side. So resist moving it. So we're going to say dy over y is equal to k dx, pulling out our magic integral marker. This, if we take the antiderivative of 1 over y dy, it's going to be the natural log of the absolute value of y is equal to kx plus c. And then we're going to exponentiate both sides. When we exponentiate both sides using the properties of logs, this becomes the absolute value of y equals e to the c times e to the kt. And this is nothing but a big constant, so we can drop the absolute value bars and get c e to the kt. All right, now this is very similar to if you were using c as or y as money. Let's try principal, p for principal, the amount of principal you invest. Now is it principal? So that's the amount you invest, and we'll that this is the original amount of money you invest, or this is your principal final. That's how much money you have in your account. That's going to be P original e to the KT, but believe it or not, the constant proportionality in PERT is just the rate at which you're investing in. So this will be P e to the RT. So believe it or not, this form appears in finance math here. So this is P final, this would be P original e to the RT. So we found PERT in our general solution here to this differential equation. So little did you know that PERT was a solution to a differential equation, and you were doing upper level math. And this would be the general solution. And so you have your principal final equals principal original e to the RT, which is pretty cool. Moving right along, let's amp up the difficulty a little bit. Actually, this isn't that difficult, but let's see. We'll move the y over. dy over y equals x dx. I just wanted to do as many examples as I could in a short period of time here. So we pull out our magic integral marker and we get the natural log of the absolute value of y equals x squared over 2 plus c. To solve this, we have to exponentiate both sides. When we do that, we get absolute value of y equals e to the c times e to the x squared over 2 using our properties of exponentials. And we can drop the absolute value bars and say c e to the x squared over 2. And this would be our general solution. Another exponential with a twist with a square in its exponent. All right, I like to do one where the variables aren't what we expect them to be because they're not always x and y. So let's try one that has u and t. And I'm going to have a differential equation here that's du dt equals e to the u plus 2t. And I have to separate the variables somehow. So in order to do that, I'm going to say du dt is equal to e to the u times e to the 2t, because I can split up this using the properties of exponentials or exponents. And now I'm going to separate and integrate. So we're going to say du over e to the u equals e to the 2t dt. And we're going to pull out our magic integral marker. There it is. And this is really e to the negative u du. All right, and we can integrate this side. This is e to the 2t divided by 2 plus c. And now when you take the integral of this, you can use u substitution, but I already have a u, so we're going to use a double u substitution. So we'll say w equals negative u, dw equals negative du, negative dw equals du. And so it's negative integral e to the w dw. And so that's just e to the w, negative e to the w. So that means we're just going to make this negative e to the negative u equals e to the 2t over 2 plus c. I'm going to multiply everything by a negative number. So we're going to get e negative 1, e to the negative u equals C, because C can be, I always keep my C's positive because -1 times a constant is still a constant. Minus e to the 2t divided by 2. And now I have to take the natural log of both sides. And we're going to say the natural log and when we do that, we can bring this negative down, negative u exponent down in front. So we get negative u equals natural log of the absolute value of c minus e to the 2t over 2. And we can say our solution is y, or u equals the negative natural log, negative natural log of the absolute value of c minus e to the 2t over 2. Now, some people don't like to have a negative in front of here. So what we can do is raise this negative up to the exponent here, and we can say that u equals, we can say or, natural log of the absolute value. And when you put a -1 up here, that means all of this is going to go in the denominator. So it would be 1 over c minus e to the 2t over 2. And then I could multiply everything by 2 over 2 and get u equals the natural log of the absolute value of 2 over, and if I multiply everything by 2 over 2 inside of the log here, that's going to be a 2 in the numerator, and then the 2 cancels out down here, and then 2 times a constant is still a constant, so it can have the same form here. So you could see this in many different forms. All right, kind of an interesting one. But still separating the variables. We got the u's on one side and on one side and the t's on the other, and then separated and integrated. Easy process. All right, amping it up one more time. Sometimes you don't have factors and you have to create them somehow. And so to create them here, anybody got any ideas? Oh yeah, I hear somebody in the back saying factor by grouping. All right, so we're going to factor the right side by grouping, because then if we do that, then we'll have factors on the right. And I'm going to select the factors as 1 plus t, and then I'm going to factor out a negative x out of here. And then we're left with 1 plus t. And then dx dt is equal to 1 plus t I can pull out in front. And then we're left with 1 minus x. And now we have two factors, and I can separate the variables. So we're going to bring the x's on the left. So it's going to be dx over 1 minus x equals 1 plus t dt. And now we can pull out our magic integral marker. And this is going to be, now I'm going to have to let u equal 1 minus x. Du here is going to equal negative dx. Negative du equals dx. And so I know that this is going to be the integral of negative 1 over u du, which is negative natural log of the absolute value of 1 minus x. Because the du here is negative, we have to have a negative out in front of the ln here. And the right side's pretty easy to integrate. That's going to be t plus t squared over 2 plus c. Now, in order to exponentiate, I have to have the log all by itself. So I'm going to multiply everything by -1 and get natural log of the absolute value of 1 minus x equals c minus t squared over 2. And now, remember, c is a constant, and -1 times a constant is still a constant. I like to keep my constants positive. So we're going to go e to the exponentiating both sides. I get the absolute value of 1 minus x is equal to, I can bust this up now because e to the c is just a constant. So we're going to get e to the c times e to the negative t minus t squared over 2. Now I could have busted these up, but they're both in terms of t, so I'm going to leave them like this, okay? And then I can drop the absolute value bars because I can make this constant a c, which will absorb the plus and the minus. So I get c e to the negative t minus t squared over 2. And now I've got to solve for x instead of y because my function is going to be of x. So we're going to get negative x equals c e to the negative t minus t squared over 2 minus 1. And then multiplying by negative 1, everything by, I can say that this is now 1 plus c e to the negative t minus t squared over 2. Now, why did I keep this a plus? Because constants can be plus or minus, so I like to keep my constants positive. All right, and this here is the general solution. So sometimes you have to factor the right side in order to get a set of factors that you can separate and then integrate. All right, let's do one where I'm giving you an initial condition and a differential equation here that's not quite solved for the differential equation yet. So what we're going to do first is take this differential equation here and find the general solution and then plug in the particular solution to find the c that goes with it. So first we have to solve this equation for dx dt. And doing that, we're going to get dx dt is equal to 1 over x e to the negative t. And I'm going to now separate the variables. So when we do that, we're going to multiply both sides by dt, and we're going to get x dx equals 1 over e to the negative t dt. All right, and when I do 1 over e to the negative t, that is essentially just e to the t. So we can make this x dx equals e to the t, which makes things much easier when I integrate. Here we go, pulling out our magic integral marker. Integrating both sides, we're going to get x squared over 2 equals e to the t plus c, e to the t plus c. And solving for x here, we multiply everything by 2, we get x squared equals 2 e to the t plus c, because 2 times a constant is still a constant. And now I have to solve for x. To take the square root of both sides, I'll get two solutions. I'll get a positive solution, which is x equals, whoops, let me take the square root here so we have some room. The square root of 2e to the t plus c, or x equals the square root of, or the negative square root of 2e to the t plus c. Now, our problem gives us initial solution 0, 1. So I'm going to solve, this is the general solution. I should say general solutions. And now we're going to solve for the particular solution using 0, 1. And it's nice to tell the grader, you know, what you're doing. And since the y is positive, I'm going to use the positive general solution again. So we're going to say y is, or x is 1 equals the square root of, now t here. So this is going to be t comma x, because that's what point we have. So this will be 2e to the 0 plus c. So we're going to square both sides and get 1 equals, e to the 0 is just 1. So this is going to be 2 plus c. C equals negative 1. I didn't mean to have the same kind of example, but that's what it is. So our particular solution is going to be x equals the square root of 2e to the t minus 1. This is our particular solution. Passing through 0, 1. All right, now I'm going to show you how to do this on my program. And we are going to, I want to view the inventory. see here. Where's inventory? There it is. I need the inventory. And I'm going to switch up this differential equation, editing it. And the differential equation was parentheses e to the x divided by, Mrs. Program likes to have divided by x. And I'll leave the color the same. Some parentheses here. Sorry. I love how this program tells me that. Okay, good. And here we go. There's the slope field. And we want to pass through the point. I'm going to edit the point 0, 1. And we're going to put our particular solution. We'll edit our particular solution. We said it was the square root of 2e to the x, well, t in our case, minus 1. And we're going to graph it. And there it is. It does pass through. And it, I wonder if that's the right slope field. I'm not happy with that. So let's see. My dy dx should be, if I look back here, let's see. Sheet 1 over x, and that's e to the, oh, wait, it's really 1 over y. Okay, I need to switch that. So let's look at our slope field here. I need to switch this. This should be 1 over, edit. Y. I like that much better. There we go. Now our slope field matches. I got a little bit lost in my X's and Y's and T's and X's, but there it is. There's our slope field and it matches, which is really, really, really cool. All right. So let's do one more solution, one more, because I can never leave any of the trig functions out. This we're going to separate and integrate. And what's interesting about this one is it has a +1. So this one, this side is the entire factor. So we're going to have to move the whole thing over. So it's going to be dy over y squared plus 1 equals dx. And then we take out our magic integral marker. And when we do that, we have to integrate the left side, and that's dy over y squared plus 2. Now, whose derivative could that be? Well, wait, I hear someone in the back saying inverse tangent. And you would be right. Inverse tangent of y is equal to x plus c. Now, we have to solve for y. Well, in order to do that, I have to take the tangent of both sides. Doing that, this will be y equals the tangent of x plus c. And that would be our general solution. Which is nice. And now they're giving us an initial condition. So we're going to solve for our particular solution using the point 1, 0. And using 1, 0, I'm going to say y is 0 equals tangent of, well, x is 1. So this would be 1 plus c. So how do we solve that? Well, gosh, when is the tangent equal to 0? Well, the tangent is equal to 0 when the angle argument is 0. So I'm going to say 1 plus c. When this is equal to 0, then the tangent is 0. So I can say that the tangent of 1 plus c equals 0 when 1 plus c equals 0. So c equals -1. So my particular solution is going to be y equals tan of x minus 1. Now, let's use my program and see if we are accurate. We're going to edit our derivative, and I promise to do it right this time. And that's going to be y to the second plus 1. There it is right there. And we're going to edit our point that we're going through. And the point we're going through now is 1, 0. So 1 tab 0 Okay. And we're going to edit our particular solution, which was tangent of x minus 1. Now, if you look at this, this is not a function. Well, this is a function, but it's not continuous, is it? And for a solution to a differential equation to be legitimate, the function has to be continuous, and this one is not. So in order to make this continuous, I'm going to have to edit my domain here. Okay, that's all right. I'm going to have to limit my domain. I got to remember how I do that on here. Let's see. Well, anyway, I'm not sure, but you'd have to limit the domain. And I took the liberty of already doing that, and I don't remember how I did it right now, but that's what the function would be right there. And it passes through our general solution, which is really, really cool. All right, another more difficult one. Sorry, I just wanted to give you as many solutions or practices as I could here. All right, gosh, this one looks a little bit scary, but not really. We got to solve for dy dx. So I'm going to solve for dy dx by subtracting x first and dividing by this factor, which would be 2y, the square root of x squared plus 1. All right. So I just moved the x over and divided by all of this. Now we're going to separate and integrate. And so to do that, I'm going to just move the y because I want you to leave the constants over there. So this is going to be dy or y dy equals negative 1/2. Because I like the constants over here. Hold on, we'll just rewrite it this way for now. We'll say negative x over 2 root x squared plus 1. All right, now we're going to take our magic integral marker out. And we're going to get y squared over 2 equals, now this one's a little bit more complicated here on the right. Oops, I left my dx off. We're going to have to use u sub here. And we're going to let u equal x squared plus 1. And du is equal to 2x dx. Du over 2 equals x dx, which I have an x dx in here. So I'm going to pull out a negative 1/2 right here. The negative 1/2 I'm going to bring out in front and then show you this, that this is what I'm integrating here. And then I have to multiply by 1/2 to replace the x dx with du. So this would be negative 1/4 out here, the integral of u to the negative 1/2 du, which is going to be negative 1/4 u to the positive 1/2 times 2 plus c. And that's going to be negative 1/2 of the square root of, well, what is the u? U was x squared plus 1 plus c. And this is equal to y squared over 2. And then we're going to multiply everything by 2, and we get y squared equals the square root of x squared plus 1 plus c. All right. And now we're going to solve for y. We're going to have two solutions. We're going to have a positive solution, which is positive square root of the square root of x squared plus 1 plus c, or the negative solution, which would be y equals negative the square root of x squared plus 1 plus c. And we want the one that's passing through 0, 1. Because that's what they gave us up here. So to do that, we're going to solve. And since y is positive, I hate to keep using the positive one, but we're going to put it up here. So it'll be 1 equals 0 plus 1. The square root of 0 plus 1 is 1. So this would be the square root of 1 plus c. And squaring both sides, I get 1 equals. No, wait a minute. This is I made a mistake up here. Hang on. I'm going to go back here. This is negative, negative, negative. So this is negative here. This is negative. This is negative on the inside. So when I this is negative 1. So when I square both sides, I get negative 1 plus c. C equals 2. Sorry about that. See, what happened was is that I forgot this negative when I multiplied everything by 2. This is still negative here. So my solution is going to be the square root of negative root x squared plus 1 plus c, or y equals negative square root of the square root of x plus 1 plus c. All right, so my particular solution here is y equals the square root of 2 minus the square root of x squared plus 1. And that's going to pass through 0, 1. And let's check it out. We're going to edit our dy dx here and say negative x divided by parentheses 2 times y times the square root parentheses x to the second plus 1. Close the parentheses there. And then close the denominator. And there we go, is our slope field, and our point that we're passing through is 0, 1. Okay, and then our particular solution, we're going to edit and say square root of 2 minus square root of x to the second plus 1. Close the square root. Close the square root again. Oh, it doesn't like that, huh? Oh, I know why, because we have to make it a 2 in front here. Sorry. It helps if the inside of the square root is not a negative number. So there's our particular solution passing through the point 0, 1. All right. So those were 2 difficult ones, and I apologize for the mix up there on the negative. Happens to the best of us. All right. You might see an equation or a problem that states another type of a problem, which states determine whether the given function is a solution of a differential equation y double prime minus y equals 0. Well, so they're giving us a solution, and they want to know if it is a solution to this equation. So in order to know if it's a solution to this equation, I need y prime, and in this case, that's cosine x, and then y double prime, which is equal to negative sine x. And I'm going to take these things and plug it into this differential equation and see if it solves it. So y double prime is negative sine x. So we're going to say negative sine x minus y, which happens to be sine x, is equal to 0. Well, is that true? This is negative 2 sine x is equal to 0. Now, this isn't true. So this is not true for all real numbers. But it is true for some real numbers. When will it be true? That's when sine x is equal to 0. So this will be true when sine x equals 0, which is x equals pi n and an element of the integer set. So this is not for all real numbers. It'll only be true when x is equal to some integer multiple of pi. So that's interesting. All right, so let's try the second one. So it's true for these. So y prime here is equal to negative 4e to the negative x, and y double prime here is 4e to the negative x. So let's see if this fits into our equation. So y double prime is 4e to the negative x minus y, which is 4e to the negative x, equals 0. So 0 equals 0. So this is, so we can say, therefore, y equals 4e to the negative x is a solution to y double prime minus y equals 0 for all real numbers, which is kind of cool. Last but not least, let's try this one. Y prime is equal to c e to the x. Nice, right? Because e to the x is our favorite function. Y prime double prime is equal to c e to the x. So let's see if that's our solution. So we can say y double prime minus y equals 0. So y double prime is c e to the x minus c e to the x equals 0. 0 equals 0. So we can say, therefore, this is true. Therefore, y equals c e to the x is a solution to y double prime minus y equals 0. Now, this is a second order differential equation because it has a second derivative in it. But so any exponential, it looks like it's going to be, for all real numbers, a solution to the differential equation y double prime minus y equals 0. So you might see an equation like that. All right, well, that's the end of my intro to solving differential equations by separation of variables. Have a great day, and we will talk to you soon.